Everyone, so we're looking at class number 12. We are going to determine the shape of a displacement versus time graph for a falling object. Okay, and what we found out is it ends up being an accelerating object. Okay, so what does the displacement versus time graph look like for an accelerating object? It's kind of where we got at for this class. So the first thing we do is just kind of go back to some review, if you will. It says, there's a typo, but it should say find the slope of a displacement versus time graph to the right. What does the slope of the graph represent? So let's find the slope here. Let's see, let's just do rise over run. Let's do something easy. Let's go to like 3 and then up here. So we have like 6 meters and 3 seconds. All right. So slope equals rise over run. 6 meters over 3 seconds. So let me just double check my math there. Yep. So it ends up being 2 meters per second. Check that out. Look at the units there. The units tell you what the slope represents. The slope of D versus T graph is the velocity. Meters per second. There it is. So the slope of D versus T graph is velocity. That's something you've seen before. So in this lab, or this, not lab, but activity, we checked out a video. We took some data from the video. And we had to establish like a time offset, like what time did I drop the ball? That way, like the time I drop it would be the new 0 time. We had to subtract that 2.8 off of each of these subsequent times. We took some data, we plotted the data. This part I am not going to go over. I'm pretty sure everyone was here for class. If you do have questions about this, please see me for extra help. We can talk about graphing. But here's the graph, so pause the video here if you're curious as to what the graph should look like. If you're curious as to how we got these times, remember we checked out the video, looked at the timestamps at the bottom of the video, not the YouTube timestamps, the timestamps that I put in the video to figure out at this time, the time offset when the ball was dropped, and then subtracted that time offset from each of the subsequent times to reach these different distances. All right, we get this nice shape of the graph. Now the graph of the data should look something like that in a perfect world. How would you describe that shape? So we heard some really good stuff from our classmates. We heard words like exponential. I heard polynomial. I heard quadratic. And in a non-math term that I really like, I heard curved. Okay. So looking at this picture, the question is the slope constant? Because we know the slope here represents velocity. But is the slope constant? Is the velocity constant? That's our question. Well, let's look here. Well, we have to make a claim. It says here, is the slope constant? Make a claim. So our claim is, before discussing with your classmates, what do you think the answer is? Think of your reasoning. So I'm going to say, it doesn't matter what you pick here, just put down a claim. I'm going to say, it is constant. All right, so let's conduct an investigation. There's a few different ways to do it, but one of them is really mathematical. So what we're going to do is we're going to pick 2 points, all right? We're going to find the slope between them, all right? Then we're going to find the slope between 2 later points, all right? So let's try that out. What we can do is I can find the slope between these 2 points here. So I can do rise over run for these 2 points. So let's see, rise would be 0.2 and run would be 0.29. So we have slope of first 2 points, which would be 0.2 meters over 0.19 seconds. And you get about 1 meter per second, about. Now, if we pick 2 later points, let's pick like the last 2 points. So the last 2 points, it goes up by 0.4. So it'd be 0.4 would be our rise right here. And our run would be 0.06. So 0.4 over 0.06. Let's see what that comes out to be. I need to get my calculator out. So we have 0.4 divided by 0.06. We get 6.66 meters per second. Notice how the slope changed a lot. Okay, slope changed a lot. Another way you could have done it was visually. You could have physically drawn the slope. So for example, you could have drawn the slope like right here and said, okay, I could see that slope, whatever it is. And then you draw another slope in right here. Clearly, that changed a lot, okay? So that's another way to do it, just like a visual way. Decide the results of your investigation, support or refute your claim. Well, the slope changed. Therefore, those three little dots instead, therefore, claim was wrong. That's okay. So our new conclusion is that the slope is not constant. All right. So just to recall really quick, what does the slope of a displacement versus time graph represent? Velocity. Why can we conclude that the velocity of the object is changing? Well, the slope represents velocity. Okay, with me there? We also established that the slope, I'm going to write it down here, slope is changing. Therefore, all right, so if slope is velocity and the slope is changing, the velocity must be changing. In physics, we call changing velocity acceleration. All right? So, how would you describe the motion of an object with a linear displacement versus time graph? Looking up here, linear displacement versus time graph. I would call that constant velocity because it has a constant slope. So how would you describe the motion? Constant velocity. Okay, because it has constant slope. The acceleration is equal to 0 meters per second squared. That's the unit for acceleration. How would you describe the motion of an object with a curved displacement versus time graph? So I would say it has a changing, sorry to squeeze this in here, changing velocity because changing slope. The acceleration does not equal 0. All right, so let's look at some graphs here. A cart travels with a constant non-zero acceleration. So don't get confused by that constant. It is very much accelerating. It's not 0 along a straight line, which graph represents the relationship between the distance and the distance the cart travels and time. Well, we know it's got to be curved, right? Curved means it's accelerating on displacement versus time. So it can't be this one and it can't be this one. So which one could it be? Well, it's going along a straight line. So this here would imply that the distance decreased. That never really happens. I mean, displacement could decrease if you go backwards, but distance is always going to increase. So this is just an invalid graph anyway. So it would be this one here, very similar to the graph we saw earlier. Referring to the diagram above, a cart travels with a constant velocity. Okay, so constant velocity along a straight line. Constant velocity, constant slope, acceleration equals 0. Which graph represents the relationship between the distance the cart travels and the time of travel? Well, we have to have a linear one, so it's got to be 2 or 4. But remember, as something moves, its distance goes up. Distance goes up, rather, so it'd be choice 4. Choice 2 would imply that distance could possibly go down over time, and that wouldn't happen. Right? So if you have any questions, let me know. Other than that, have a great day.